It's a big pleasure to present you to Marc Timme, who's a chair of network dynamics group in Technical University of Dresden. But I will let Marc present you and tell us more about actually your group and your research. Inverse problems in network dynamics. Floor is yours. Thank you for coming.
Thank you much, and in particular to the invitation to Paris. I would have liked to actually come in person, and maybe I get the chance at some point if the pandemic permits it. Yeah, I'll talk today about inverse problems, and if you are not familiar, I will give some introduction, but generally it means to get a model out of data. So typically as a complex systems physicist, you are handed some model and maybe you introduce some new parameter and then investigate what comes out of the model, what kind of dynamics you find, for example, and how it changes with varying parameters. And we are taking the other route now. We start with phenomena and deduce features of the model. And this is work with José Casadiego, who was a postdoc with us, and he's now in Spain. Joachim Peinke is a physicist in Oldenburg. Hauke Hähne was Joachim's and my student, first mine as a master's and then his PhD student. Malte Schröder is a team leader in our professorship. Nora was, some of you know Nora, I think. Nora was a postdoc with us for a few years, first in Göttingen and then in Darmstadt and then actually in Dresden. David is a PhD student currently finishing. Philip Marshall is also a PhD student, not yet finished. Yeah, so I run because I have to keep time. So you all know networks and they come in different versions: social networks, neural circuits, gene and protein regulatory networks, chemical reaction networks, transport and distribution networks. And in most cases, they are from different realms of disciplines, of traditional disciplines. What we are focusing on is basically natural science and engineering with some parts of socioeconomic systems. And today I'll focus on inverse problems, as I mentioned, which was originally motivated from biology, but it goes more and more into the engineering and physics piece of our work. And I will also briefly mention at the end of the talk something about network public mobility. So what happens if you introduce communication or coordination in large fleets of mobile, either agents in some way. So either people or cars or both. I have to move myself. Otherwise I don't see my own slides. So the standard view of a system is you have some black box, and if you're a theoretician or an applied mathematician or a modeler in general, you want to do a model. You build a model, or you have typically given a model. And as I mentioned, sometimes you add new parameters, and then you are interested in predicting dynamics. And what does it mean to predict dynamics? In the simplest case, it's just a system, and you just observe what the system does on its own. Or more generally, you may drive the system with some input and you predict the response of that system to the input. So it's somehow a mixture then of the system properties and of the input. So you have a model of the system constituents. And if you're talking about a network, you have a model of the network structure, topology, dynamical coupling functions, and so on. And you want to understand dynamics, for example, what are fixed points, which fixed points are stable, what kind of other dynamics you may have, periodic orbits, chaotic dynamics, and so on. What are, for example, response functions if you have an input? What are bifurcations? Which parameter do I vary to get from one to another state, and so on? What are basins of attraction? All kinds of these questions are forward standard problems. They might be very hard, but they are all in the same direction. So you have a model, you want to know what the model does. But how to obtain a model for a given system is a different question. So there are essentially two ways. You take it from literature or you expand it somehow. So essentially you take it from someone else and you play with it. Or you do it yourself, which means you have to use some constraints, and the constraints are data. They can be all kinds of data. In the simplest case, they are time series, or you have even less knowledge. You have just some features of the model, and then you try to build the simplest model which reproduce all you see from the experiment and still is consistent with everything you know. So there's a review by Jose and me in 2014 about mathematical models of how you, like ordinary differential equation models, how you get, how you view this inverse problem and how to make progress if the inverse problem comes in form of a differential equation or a system of differential equations. So again, inverse problems, you have the observation, you have a system, you have the observation and the input, but you can't see the system, or at least you cannot see some properties of it. So you want to deduce from knowing the input and possibly knowing the output and possibly the input, you want to deduce what a system model is, or you want to deduce some features of that system model. So typically you can't find one exact model because you are under constraint. So you want to understand some features. So you observe system dynamics and you deduce system constituents. And if you have a network, some topology, you observe the network dynamics and you deduce network constituents, which might be the units, the links, coupling function, local dynamics, and all kinds of that. Maybe delays, whatever you are interested in. Which features are most essential if you have a networked system? And I drew the sketch just as a sketch actually and on purpose I did it in an abstract way because you more or less see what is most essential. Arguably the most basic feature of such a network is the network size. Like how many nodes do I have in a system? Imagine you stick an observable, you just record some collective quantity from it, and you want to know how many nodes or how many variables do I need to describe this full system. And we have worked with Hauke and Joachim Peinke on this problem, and Jose. Finding network size, or in general, if you have multi-dimensional individual units, you can argue that it's about the number of variables in my system. And the second equally or almost equally essential feature is interaction topology. So who interacts with who? The question is, can you get out the network structure if you don't have information about it, or you have only reduced information about it? And for both of these questions, I'll spend a couple of minutes explaining the problem and explaining one possible way of going forward. So I start with this one, finding network size. So imagine you have a network and you can observe only a few of the nodes, but you really can only observe the nodes. You can't see the links and you can't see a number of other nodes. You just say, okay, I can record from, so okay, for example, you can imagine you're talking about a gene regulatory network. I just can measure the concentrations of a certain number of genes and possibly proteins, which regulate the genes. And I don't see all of them, and I also don't know how exactly they interact. So then you would perceive some signals, time series, from small n units. And units here stand only always for number of variables, okay? And you can, there possibly is some input, but it's not essential here in the argument. So I name the vector of all units or all variables, I name x of t, and the perceptible ones, those I can actually record from, I call y. So y is a subset of x, okay? So as I mentioned, the basic question is, what is the number of variables, or what is the network size? How many nodes do I have if I have individual one variable per node in the simplest case? And the idea is like this. You have a given recordings. You can repeat the recordings, for example, from different initial conditions, or you drive the system and record them. And you repeat it, and each time you collect the multidimensional time series you get into a matrix. I'll tell you how you do that in a minute. You collect different realizations and you can argue, okay, if you start from generic initial conditions, for example, you would have linearly independent vectors you store in your matrix. And then, of course, if you have stored more than n, the number of variables you have here, total, including the non-visible nodes, trajectories, then it can't be linearly independent anymore, right? Because of that, you would see, if you add more and more trajectories, you would see an increase of the rank of that matrix until the full rank is achieved. So at some point, you can't increase the rank anymore. So you would see a growing rank, and then it settles to some constant. It's not quite true as you'll see in practice, but this is the basic idea, okay? So first you collect different sample trajectories of each perceptible state in time and across the nodes. So in time here and across different nodes colored here. You suitably arrange those data into a detection matrix, and I tell you what suitable means and what detection matrix actually means. And then you exploit that this rank is at most equal to the system size, the number of independent variables you have in the system total. So for explaining the idea, I start with the simplest imaginable system. You have a linear, noiseless relaxation dynamics towards a stable fixed point. Okay? So you start with some nonlinear system, z dot equals f of z, and you take a stable fixed point of that system, where f of z is 0, so you can linearize about it. You get a linearized system for the new variable x, which is my full vector. But remember, most of the components you can't even record. And also you have no idea what f is or what a is. So a is just the Jacobian given f, but as you don't know what the system is, you also don't know a. You just assume such a thing exists. Then if it's linear, because it's linear, you can formally solve for x of t. Okay, you just integrate this equation with the constant a, and you would find x of t is matrix exponential of at multiplied, so this is a matrix again, multiplied by x of 0, the initial condition. And that's an n-dimensional vector. Not surprising, and we all learned that in our studies, I think. So now you observe only if part of the components of x, which I call y. So this is a matrix which consists of a small n by small n identity matrix, and the rest is zeros, okay? You just project out only those components which are relevant for you. Then I can write it in this form. yi of t, each component I, as a function of t, is a sum over time-dependent weighting factors, which we call theta ij, times xj of 0. So now for us here, because you have the exact solution, theta ij is just the matrix exponential component ij, okay? It's just the rewriting of the line two lines above, and I ignore all those x which I can't observe, and I get these equations. So the catch here is this one, independent of how theta actually looks like, because we don't know it anyway. This is the functional form is always the same. So for all kinds of systems, independent of how it looks in detail, the functional form would look like this. You have a observed component, and you have the system components, and somehow they couple, but you don't know how. And let's go into more detail. So we assume we have m time series, m different recordings and experiments out of n perceptible units. We call, for simplicity, we just label them 1 to small n, and then the other n, the n plus 1 to capital N, are not perceptible. You can't record from them. And you sample them at k time points. You could do that differently in each experiment, but let's not do it. Okay, if it's constant for each experiment, it's just simpler to present. So that's the same thing, just rewritten. Now you can collect the m's measured trajectory as a vector. So this one is a vector under condition m. So you can imagine that, for example, for each small m, you have one particular initial condition, and then you go back to the system next day and you find it in a different initial condition, measure again with the same theta, but you don't know the theta, and also you don't know the initial. You know some of the initial condition, but not the entire vector. So then you collect these vectors into a matrix. So you take the second dimension and you collect it across all these m's. So here we collected across components. We could now collect across recordings, like experiments. And then we rewrite this equation as a matrix equation. So there are three matrices now. Y is a matrix collected in both dimensions, units and trajectories. Theta is a matrix, and x0 is also a matrix. So then we collect even more, or we rephrase it a bit, such that the T on my matrix I want to treat is collecting components of Y. So Y is a matrix, okay, at different time points. So now I sampled it, and at each time point I get one matrix. I transpose it, I collect them, and transpose again. So essentially, I collect together matrices Y at different times. And then again, I rewrite it as in this form. So this T, which I call detection matrix, is given by a theta, which is also some matrix, just theta evaluated at different k times tk, t or t whatever, tj from 1 to k, times x0. And the only thing which is now a constant and not dependent on k and m, the number of time points and the number of trajectories, is x0, okay? But x0 I don't know, or I only partially know. So this equation, well, there's this linear approximation, but beyond it, this equation contains all information that I have from all my measurements, okay? I assume I'm somehow near a fixed point, stable fixed point, and I just collect the data. And the data here on the left are on the left-hand side of my equation, and the right-hand side, most of it I don't know. This one I don't know entirely, and this one I don't know most of the components of. Okay, so pictorially it looks like that. You have a matrix which you want to know features of, but actually it's all the data you have, and then there are two unknowns. And of course you can't solve for anything because you just don't know any information except the left-hand side. So the question is now, can you deduce the network size from the one matrix TKM? And the idea is to exploit this rank inequality, as I mentioned before, that because you know it is of this form, although you don't know any of the components here, you know it's of this form. So the only thing that can formally happen here is that the rank of the left-hand side, this is true for all, it's just a linear algebra inequality, okay? The rank of this guy is always smaller than the minimum rank of these two because it's a matrix product. So this means you can increase the number of trajectories you take into account. So you could collect everything and then take one by one and increase the size of your detection matrix one by one. And you would observe, most likely would observe, initially an increase of the rank of T, but at some point you wouldn't. And if you see here, there's N, capital N, the number of units in your system or number of variables in your system in both of these matrices. No? So if Kn is large enough and M is large enough, both larger than capital N, you are certain that once that the rank of T stops growing the moment you reach N, okay? Because that's the minimum of these two. And that's actually what's happening. So you increase the number of trajectories taken, or experiments taken into account, and divide by N just for simplicity, so you can present different network sizes. And so you see an increase and a leveling off. So remember that you measure only a small fraction of the units. I think here it's I don't know the number, but so you measure a fraction of the units, and it exactly gives you the network size, the number of variables. So imagine, by example, you measure from 27 units trajectories repeatedly, and at some point you can say, if you have measured enough, you can say, look, the system has 152 nodes. Okay, so although you measured only from 27 of them, and this one is the same, just linearizing on a periodic orbit of a linearized phase oscillator system. So this is like Kuramoto-like system. I don't go into detail. The question is how to find, how to quantify that, and we do that by detecting a gap in a singular value spectrum. And in the simplest case, it's a gap detection like that. So it's a very large gap on the logarithmic scale. And you know that at some point, the single values of t stop continuously varying, well, almost continuously varying, and just jump to essentially numerically 0, at which point you are sure that this one is a system of n equals 100, which was our example. And you can, of course, do that as well for the oscillator, phase oscillators. It's a bit smaller because it's just linearized. The original system was linear, so it's perfect in a mathematical sense. This is an approximation, but you still see that the same method works here as well. Now, of course, most systems are not near stable fixed points, but they are somewhere, okay? And now let's do it for somewhere. You consider nonlinear dynamics, and you don't care at all at which point you are linearizing about. Now you're wondering, of course, you have to somehow constrain it, and yes, you do constrain it. You constrain it by your data. So if you have data in this piece of state space, you have a lot of trajectories going on there, you just take any point near the data you have, okay? And so I take this arbitrary point, Z star, then I can evolve my system in time. Z of t is phi t z of 0. You compute the difference vector between two trajectories, and then forward evolve the linearized system near that point. Okay, it's not even a fixed point. Z star is just some point in state space where I have trajectories nearby. I linearize the flow. I have a time difference. It looks complicated, but it's actually very simple. This is the linearized version of whatever this flow is. And again, I don't know it, right? I don't care. I just care that this one has the same form as before. So this time I take the theta ij of t, which appeared in my transformation matrix, as the derivative of the flow, which I don't know, with respect to z, most of which I don't know. So it gives you the same form as before, and by that trick you can apply the same method to other systems. For example, to multi-dimensional periodic systems and even to chaotic systems. And here there's an example where you apply, you have a system which simultaneously has noise, the system is sparse, and it's heterogeneous in the sense that the weights of the coupling strengths are very different. Here somehow gray coded, okay? And you see it's not perfect, but it does saturate and it gives you the right number if you measure long enough. So this is a minimum number of, frequently enough. This is a minimum number of experiments you need to do given some noise strings. With that, I'll switch to a second part. It's about model-free network inference. You have given again a nonlinear network dynamical system, and you want to derive a linear system of constraint equations. Then you apply group sparsity, and you map out the right connections without knowing anything of f. Okay, we have no clue what f is. We just record x of t, and I give you back the network. Okay, first we have to clarify something. Although by this simple model system, although these equations all look the same, there's a pronounced difference in the third equation because this coupling depends on two other variables. So here variable is x3, but the coupling depends on x1 and x2. influencing x3. So this one is a genuine 3-point interaction, which is uncommon in physics, but it appears everywhere in all kinds of other systems we like to model. So just important to keep in mind, what we know from graph theory is you can construct an incidence matrix of who influences whom. So if you look at this interaction graph, it doesn't matter whether it's pairwise coupling or 3-point. It's just an incidence whether one unit influences another. For example, here unit 3 and unit 1 affect the rate of change of unit 1, which is the first line. We define something which is very closely related to this incidence matrix, which are diagonal matrices mapping out the correct component, the components you want to identify which components of x are influencing the rate of change of xi. And here you would map out 1 and 3. So in this example, the explicit dependency matrix, how we call it, is a diagonal matrix which has 2 1s in the element 1 1 and element 3 3, and all the other elements are 0. And in general, this explicit dependency matrix is a diagonal matrix with exactly these incidence matrix rows on the diagonal. Okay, looks like that. So here the incidence matrix rows just exactly on the diagonal. I skipped why it's useful. You have to believe me. Okay, what we do here is we can now exploit this simple rewrite. So we have done nothing essentially except representing my system, which we don't know, by including this explicit dependency matrix. So now there are 2 steps of expansion. Like Taylor expansion, this is not Taylor expansion, but we expand in certain ways. The first, we expand in orders of interactions, as I presented this, for example, 2nd order and 3rd order, we do that. And as you see, the components of the explicit dependency matrix appear in any 2. Now, this is like an influence from J to I, and it appears in a 2-point interaction, it appears once. In a 3-point interaction, which is 2 new variables, it appears twice, and so on. So we expand this. The only thing we are looking for is essentially lambda. So we want to know who is influencing whom. And what we don't know is the g's. None of the g's we know. This is just a completely formal expansion because we don't know f. We have no clue, okay? So, but the important factor here is that the lambdas now appear as linear coefficients in this equation, okay? That's the only take home here. You expand, you get linear coefficients in a very complicated way, and still the g's are not known. Now you expand the g's in some basis function. And I don't tell you what kind of basis function. We just pick some, okay? The basis functions are called h, j, and p. P is like the order. For example, you can think of polynomials, x to the p, xj to the p, for example, or sine functions or whatever. I'll give some examples later. And again, you get, of course, coefficients here. And in total, you get linear coefficients up here, all appearing in this equation. And now, because you know the basis function, you define them, you can substitute x, your recorded time series, into this function, and you will get a number. Okay, this one becomes a number. And if you have sufficiently quickly sampled time series, you can also estimate the rate of change, this one. So this one gives you a system of linear constraints, including the things we look for, and all the other things are given numbers from the data. So h is a function, x is a number substituted into the function. So again, it's a function, and also the higher order terms are all functions. So in summary, this system looks like that. It's a constrained system. I know y, I know d, I want to find c. The problem is c is not just any has not just any arbitrary structure, and also it's not sparse as commonly as assumable for networks, but it's block sparse. Why is it block sparse? So assume that from unit j, for example, there's no coupling to I, then that is true for all components. For if j is 5, all components appearing with a 5 here are essentially 0. So the entire row of components which appear in this quadruple sum are all 0. So you have large blocks of zeros, and sometimes you have something where there is an influence, and then you get a block of non-zeros. You don't know them, but you have a block of non-zeros. And to find C, we now invented an algorithm which is a projection algorithm, and it's called ANI. And of course, you know ANI, and ANI is this guy. And it's called the algorithm for revealing network interactions. And it individually shoots down possible interactions. So what it does is it takes a basis of all possible influences. So if you are talking about xi, the number of influencing units is all the other units. And you ask which single one of the other units is explaining my data best. So if I took into account only that single one, how well would it describe my data set? And we take the best option out of those and remember that one, okay? Then we project out the influence of that component, which is illustrated here. You project it out, and then in the output, in the space projected out, you take the next best component. So given that this one is the best explanation for one component, what is the best of two influences explaining the data, given that the first is the red one and the second is a green one, so it's some other unit. And we go on, and then there's a threshold condition, stopping condition, which I won't explain, but the interesting thing is that it's completely data driven. So here you see, you can measure some error measurement, which essentially tells you how well your data are explained by the chosen approach, independence of how many units of interactions, like pre-connections, how do you call it, in degree. So if the in degree here is 15, for example, for unit I, then the error would go down, 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 and at some point it levels off. So you get an L-shaped, or almost L-shaped function. And if you find a criterion to decide when this kink of the L appears, you have a criterion to decide when you stop. So in this case, it's the actual system, underlying system is 15 inputs to unit I. And you see that as of 16, it just stays constant. And now it's of course not always the case, because you choose the basis function, and the basis function the interesting thing here is the basis function can come from one of two classes. Either it's like the correct class or it's a wrong class, which you see as the quality score, the area under the receiver operating characteristic curve. And if that is 1, that's a perfect explanation of the data. If that is a 1/2, it's essentially guessing. So you see that 2 of the basis function so we now take this complicated system with a sign of the phase difference and phase shifted, and a sign of 2 times the phase difference. If you take basis functions A or D, it doesn't explain it at all. It's just like you could have guessed or just scrambled the data. If you take any of the other basis functions, for example, the correct one, which is a sine and cosine basis with multiples p, or this one, the product of 2 exponents of x, or the exponent of a difference of x, all of which explain the data quite well. So B, C, and E. And so the conclusion is only the type of the basis function explains your data, you don't need to have the right basis function. Otherwise, you would need somehow a model. So you have to actually only know what is the order, like what is the correct order. And here the order is 2, because you have a double influence onto I. And so you need something like that. This one is not sufficient. It's always the interaction between I and J to influence I. It's not only J in itself. And that's why you need two interaction functions here in B, C, and in E. I don't know whether you should still present anything about mobility, Yuba.
Well, I think that it's better to kind of come to the more conclusions part, because then we will have more time to discuss. And
so
yeah, mobility will be great.
all the mobility things, which I want to jump over anyway.
It can be good, Yuba, to have some empirical aspects, maybe, no? I think.
I don't know. I can also only, let's do the following. Let's do the following. I only explain the problem, okay? Like 3 slides, okay?
I think it can be useful, actually, to kind of get a grasp on like the application of that.
It's not a direct application of that, but it's also something of how to find a model, okay? It's related, not the same. You know probably better than me, or at least have more experience in Paris and in Dresden about complications in mobility, not least in the climate change era. Future solutions hold lots of promise. They want to be more flexible, more shared, more electric, more autonomous, more cost conscious, more intermodal, more interactive, and more networked. And that's why it's a physics or data analytics problem, because you are looking for collective phenomena on the dynamical systems perspective. You want to understand and predict the system before you control them, so it's not a pure engineering approach. And the phenomena are from physical systems, as I briefly sketch now. I spent like 1 slide on each of the topics 3 times, and then I'm done, okay? So first of all, what we did is we took original data from taxis in Manhattan, and we asked when they request where a taxi, when people are requesting. And we now did a simulation with these original requests and asked what is the number of available taxis as a function of time of the day during several days. And you see that the available taxis drops to 0 at some point, and it stays at 0 very long and goes up again at some point. At the same time, the request rate goes up, but then it goes down again. So you observe here that although the request rate for example, at this point, the request rate is low, and there are still 2,000 available taxis around here, okay? But here, the request rate again is the same, but there are 0 taxis available. How comes? And we are interested in the question of how this comes. If you plot it in state space, like the number of available taxis against the request rate, you see a hysteresis. And we attempted to explain it. And one rough idea of how to explain it, I can't do that now, is that the moment there's no taxi available, each taxi needs to go empty so if you take the next available taxi, each one needs to go to the customer empty to pick up that customer. Yeah, no taxi is available. I ask for the next taxi, I get assigned the next taxi, but the next taxi is not available yet. It pops up somewhere, like say in northern Manhattan and I'm in southern Manhattan. It has to go to me immediately, but it takes 20 minutes because it's Manhattan. It's a large piece of land. So that's why it takes a lot of time. And so if you are fair, the take home here is if you are fair, then you get an inefficient system. Whether if you assign it in an unfair way, if you don't assign it first come, first serve, you get a more efficient system. So that's a contradiction between these 2 aspects. And yeah, we used spatial temporal data here. We also have worked on a related inference problem on anomalous supply shortages, which is induced by, well, we believe is induced by dynamic pricing. This is has been viewed in newspapers actually first by Malte Schröder, our team leader. He came back from a conference and said, look, there are drivers of Uber, of a ride-sharing service, ride-hailing service, and they switch off their apps according to some newspaper reports. Collectively, like an entire lot of Uber drivers would switch off their app to improve their own pricing. So if there's nothing available, people the algorithm increased the price per mile. And so the drivers would earn more if they pick a ride. So they keep it on collectively, and then on a signal, they all switch it on again. Then they get essentially the same customers, but get paid more for that. And so what we did there, just to teaser again, is to disentangle the total fare, which we recorded from the Uber API, into the base cost, like what does it cost given the traffic conditions, for example, the traffic is slower, you're longer in the taxi, so it would cost a bit more, and the search fee, like what the algorithm adds to that. And we found that you can classify places, or actually routes, like for example, you go in a given city from a given airport to the inner city, or you go from another city from the airport to the inner city. It's a different story depending on where in this diagram you sit. So given the distribution of time scales in the system, like how your time scales look like, what are the price changes over a given time, you get two distributions, one broad and one peaked, or you could just get two peaked ones, in which case you have no real search. The question is, of course, how broad it is, how weighted this is as well. So third and last example is about ride sharing. Ride sharing is a combination of the advantages of individual mobility, detours, no detours and no waiting. You can go flexibly from A to B at any time. But the problem is you have many vehicles, because each person needs to go with their own vehicle. And the total distance driven is long. For public transport, line-based, you have few vehicles, like big buses or subways or whatever, and short distances per person driven. But you have long detours for the individual users and long waiting times. And the intermediate field is ride sharing, where you hope to get a few with a reasonable number of vehicles and reasonable short distance given the trip requests. You have short detours and short waiting times. And although I don't go into details, I will show you that typically you expect, of course, that in big cities or in medium cities or in rural areas, you would get a completely different quality of service. And you can ask how efficient the service is. And again, that's only a teaser. You can somehow map out overall parameters and define a load, normalized load, which depends on the request rate and the typical trip distance and so on, and the typical velocity of a bus and the number of buses. And then you can define the number of customers in the system, which are not served yet, scheduled customers. And you would find a scaling of these customers with a load. And from the scaling, this is the left-hand side picture, from the scaling, you get an efficiency curve. The efficiency curve is like how it scales for large X. And you see that the flatter it is, the more efficient the system is. And then you would expect that of course, depends on the topology. For example, you did it for these types of topologies, and you get different types of efficiency curves. Now, we do one thing, we divide by B1/2. Like you ask where this efficiency is 1/2, and you would divide by that number, the horizontal axis. Schnips. And what happens is all of these curves collapse to one universal curve. And we do that again for real data, like real street networks. And well, the original ones look like that. You normalize, you get this. And then we did some theory, which I don't have time to tell you, but the take home here is there's a universal scaling function covering different kinds of network topologies, very different kinds, like Berlin Mitte and Corfu, which is an island, or the Isle of Man, which is an empty island, essentially, and all kinds of other places like large cities and very rural areas, all falling in the large limit, the limit of large number of vehicles, and this also means effectively large request rate, because we are talking about this X load factor. They fall on the same curve, meaning you can try to transfer a given service from one region to another if you have certain information which is much reduced compared to the full information how the details of the street network and so on look like. So you don't have to calculate everything. So I don't have time for the summary, which means I'll just thank you for your attention and my team for enduring support. Thank you.
Okay, great. It was probably a hike or something, right? That was great.
This was, yeah, if you want to come to Dresden, this was taken 2 years ago, I think, at a hike to Sächsische Schweiz, yeah.
Yeah.
Please come by.
Yes, you have a beautiful area there. That's great. Yeah.
So,
Well, I do have indeed many questions, but I wanted to ask if anyone wanted maybe to go first. If you have any maybe more questions on methods or applications or clarifications, because more I wanted to ask about the Uber and mobility more. So maybe if you could go back to the slide where you go to.
and Shakwash has a question as well.
Ah, okay. Yeah, but just if I started indeed to ask on the Uber.
Yeah, to ask the question.
Yeah.
Take
So
a few more seconds.
so the when you were recording, right? So I wanted just to understand how kind of realistic is it, right? Because the ride itself is actually right. It's recorded as a real one, right? But then afterwards you need to understand whether you would be able to like reconstruct it from the missing data. So I did not understand what exactly you were trying actually to reconstruct. I understand.
So you have a very low dimensional recording. The only thing we have is a number of rules how Uber computes costs, and so that it consists of a base cost which is time dependent essentially, and there's a one-off cost, then there's time and mileage dependent cost, and then there's a search fee. That's the one information we have. And the second is price curves.